You need a piece of paper here. Improper integrals. Here's the first thing. I want to tell you what an improper integral is not. Okay? An improper integral is not an integral that wears Bermuda shorts and a tie-dye shirt to a business party. Okay? Now, while this may be improper attire, this is not what we mean by improper integral. Okay? So it is not a poorly dressed integral. Right, that's the first thing you need to know. The second thing you need to know is it's not the integral of an improper fraction. That's not what we're talking about. This is an improper fraction because it has a higher degree on the top. It's even improper if I make the bottom x squared. You remember, improper fraction means the top is equal or larger degree than the bottom. That's an improper fraction. But an improper integral has nothing to do with either of these. So I felt it was important to tell you what an improper integral was not. It's not these. All right. An improper integral is, now there's actually two kinds of improper integrals. The first one is any integral that looks like this, where there's a number here and an infinity here, okay, or a negative infinity here and a number up here, or one of each. So improper integral, I'm not sure it's the best name, but it really just means that we have an infinity somewhere in the limits of an equation, or a negative infinity. Those are improper, okay? Another kind of improper integral is an integral that looks harmless enough. That doesn't seem to have any problems with it. Where f of x has an infinite discontinuity, or you could say a vertical asymptote, on the interval AB. Okay? And that includes at A or at B. So here's what we're saying. Okay, I'm going to draw some pictures for you so you can understand. For each of these impropers, I'm going to draw you a little diagram. Okay, you could copy the pictures with me. A little more space. Okay, here's a picture of the first situation. I've got this function, right? This curve, la-di-da, and I'm trying to find the integral from 1 to infinity. This is improper. It's improper because we're trying to find the area of an infinitely large slice of space. Okay? Now, I'm not saying there's no answer to this. Actually, in some cases, this red area does actually exist. What I'm saying is this is improper because of what it's asking for. The second one is improper for the same reason, and the third one's improper for the same reason. A picture might be something like, here's a graph. Okay, and we're trying to find all this area from negative infinity all the way out here to some value b, I don't know, negative 3. Again, it's improper because of what it's asking for. It's asking for the area of an infinitely large slice. And the last one, you might think of this very famous bell curve that some teachers use even in their grading scales. Or you've seen it in probability situations. you're trying to find all of this area. The graph is perfectly smooth and continuous, and there might even be an area, but the fact that it has infinities as destinations makes it an improper integral. So an improper integral is just an integral with an infinity in its limit, which means you're trying to find the area of an infinite large something. Now, sometimes these red areas do not exist, and sometimes they do, but that's not what we're talking about right now. This one here is, I can think of sort of three pictures for this one. This is sort of day 2 stuff, so I probably won't do any examples of this today. But imagine a situation where you're asked to find the area between, let's say, 1 and 5. That sounds harmless enough. But the function has an asymptote at 1. How are you planning to find this area here? See? Well, it turns out we can actually do it, but this situation is improper. Okay? Improper. Because we're finding the area up against an asymptote. Another one would be if you were going from a number to an asymptote. This would be the same kind of thing. So maybe you're going from x equals 1 to x equals 5 again, but there's actually a vertical asymptote at 5. So it looks like this. And you're trying to find all this area. Improper. Improper situation. Or maybe there's an asymptote sort of in between A and B. So you're going from x equals 1 to x equals 5. But there's an infinite discontinuity, let's say, right here. I don't know, at 2 or something. And you're dealing with this curve and you want to find this area. Or maybe there's an asymptote at 1 and 5, something like that. Or more than one asymptote. Okay, so these are all improper integrals because of the nature of their situation. Again, I'll say it one more time, all the red areas may or may not exist. We'll talk about that later. Okay, so that's the third slide. Fourth slide, how do you know if your integral is improper? So let's say that you come up on the AP test and you're given this problem. Problem looks harmless enough. Actually, let's make it a little bit easier. Let's put a 2x on top, okay? This problem can actually be solved. Let's put a 2x minus 4. This problem can actually be solved by substitution. It's actually not even a hard integral. Or you could try partial fractions on it or something. But did you notice that there is a vertical asymptote at 2? And that is right smack between 1 and 5? That's a problem. Would you have caught that on the AP test? Or would you have just done antiderivative and integrated right through that asymptote without even realizing it? Do you guys understand what's going on? This is very important. You cannot run this integral the way you might think. You have to be very careful with this integral. There is an asymptote at 2, and you're integrating from 1 to 5. Picture that. That's improper. And it would be very easy to miss that on the AP exam. So Hugh? Yeah.
So I thought wouldn't it be a whole at 2 if you did 2x minus 4?
Oh, you're right. You're right. There's a, well, actually, no, there's a whole and an asymptote because there's another x minus 2 on the bottom. Yeah, he's right. This factors into 2 times x minus 2 over x minus 2 times x minus 2. So it would appear to be a whole at first, but then you realize there's still an asymptote at 2. The point of this problem is, I'm not trying so hard to give you a problem to solve. In fact, we're not going to solve this one. I just want to show you that you got to be really careful with this, because you think on the AP test they're going to say something like, solve this improper integral? No, they're going to give you an integral. And you either notice that there's a vertical asymptote in the way, or you don't. So hopefully you'll see, oh goodness, there's a break in the graph. I've got to be real careful here. Okay? Or how about this one? Some people catch this kind of stuff real easily, but if I said, hey, let's find the integral from 0 to pi of cot x dx, this is an improper integral. maybe you don't know why, but the graph of cotangent looks like this. You see? This question is completely improper. You're trying to find the area in here. And it's probably 0. You know what I'm saying? It's probably 0. You've got 2 pieces above and 2 pieces below the axis. They're exactly congruent, right? But it's still an improper integral, and it needs to be handled carefully because of the asymptotes. You've got 3 asymptotes going on, right? One at the start value, one at the stop value, and one right smack in the middle. So one of the things is you have to know you're dealing with this sort of situation, okay? Now, if you see an integral in an AP test that looks like this, find the integral from 1 to infinity, 1 over x squared, that's going to be obvious that it's improper. I mean, it's totally obvious. It says infinity right there. But the other two weren't that obvious. You have to pay attention. Okay. So the next slide is you have to practice rewriting your improper integrals. Okay? This is probably the only hard part at all about this entire lesson. And even this isn't that hard. Okay, so for example, let's say you're given this problem. Before you even start this problem, you realize, hey, it's improper. And you say that really loud. Really loudly. You say, hey, that's improper. Well, then the next thing you do is you rewrite it. First you change this to a B so that it's proper. Okay, now it's proper. And then you put a little LIM, B goes to infinity out front. And now it's in proper form. So it's like magic. It's not okay to put infinity up here. But it is okay to put a B up there and then let B go to infinity.
That's really magic.
Yeah, that really seems like, it seems kind of like a double standard. We're saying that's improper and that's proper. They're exactly the same thing, right? But this is the proper form of that.
So it's not fully proper, it's just a little bit more proper.
It's actually doable. See, what's going to happen is you're going to find the antiderivative. You're then going to have to plug in these two things, and they better be numbers, you see. See the problem? This is improper because if you find the antiderivative, how are you planning to plug in infinity? It's not a number, see? So first you convert it to proper form. We're not going to do this problem right now. I just wanted to show you how to convert it to proper form. How would you convert this red one to proper form?
Limits a goes to negative infinity, a to negative 1.
Well, yeah, this is definitely okay, the upper limit. Everything's fine. So you said let's change this to an A? Sure. A just means lower limit usually, right? And then we wanted that to be a negative infinity, so what do I put out front?
Limits a goes to negative.
Exactly. Okay, here's a tough one. How about this one? This is a really hard one to rewrite. It looks so harmless, but it's got all sorts of issues.
Oh, that asymptote.
Yeah, so this thing has all sorts of issues. Maybe we could construct a quick diagram for this one so you can see what's going on. We have the graph of 1 over x, very familiar, friendly graph we've worked with for years. We're trying to find the integral from negative infinity all the way up to the asymptote at 0 and beyond until we get to 1, and then we'll stop. We got problems here. So how are you going to rewrite this thing? Well, first, you're going to have to go from negative infinity towards 0. You can't actually get to 0. There's an asymptote in the way. So what you're going to do is write this. You're going to go from negative infinity all the way up to some point near 0. So you can't put 0 there. You're going to have to just put like C or something here. So let's put C there. Okay? Let me rewrite this a little bit neater. So we're going to go from negative infinity to C, where C is a number just shy of that asymptote. And then in front, we're going to write LIM, C goes to 0 from the left. Okay? So I'm technically not going to 0. I'm going to a number just shy of 0, and then I'm letting that number approach 0. So kind of just rewriting in the proper form. Then you have your 1 over x dx. For the second integral, I'm going to have to pick a c on this side, just to the right of 0, you see. So I'm going to do LIM, c goes to 0 from the right, c to 1. But it's still not proper. Why? I've got an infinity in my limit. See? So I got to fix that too. So it looks like I'm going to have to write it like this. LIM, a goes to negative infinity of LIM, c goes to 0 left of a to c, 1 over x dx, plus LIM, c goes to 0 right, integral c to 1, over x dx. So if you're not paying attention, I have no idea how you're going to learn this. I have no idea. Like, where are you going to pick this up? It's not that intuitive. But what's going on is we can't have an asymptote, nor can we have an infinity in our limit, in our integral symbol. Therefore, we have to use limits out front instead. Okay? So notice I replaced the negative infinity with an a, and I replaced the c, which was troublesome, or the 0, which was troublesome, with a c, and I've got the limits on those to represent. This just means that c is going to be 0 and a is going to be negative infinity. And you can actually put the limits in either order, it doesn't matter. They're very forgiving. This one only had one issue. On the journey from c to 1, c was 0 originally, so I had to change it to a c and let c approach 0 from the right. So this is how you rewrite an integral in proper form. And you can imagine it would be even worse if there were more asymptotes or something like that, right? Does that make sense? Okay. Okay, the next thing is we're finally ready to evaluate some improper integrals. Now, I'm going to focus on today on just the integrals that have an infinity or negative infinity in the symbol. I'm not going to do the ones with asymptotes today. I'll just do that tomorrow. Okay? So here's my first problem. Looks harmless enough, but it is improper. Please write it in proper form. Okay, I'll pause the recording. Let me start the recording again. First thing you should have written is, you should have replaced this with a b, which is what we usually use for an upper limit. And then you put an LIM, b goes to infinity here to preserve the fact that b is going large. Now, what's the antiderivative of 1 over x? So, Chloe, what's my antiderivative for 1 over x? Yeah, and we don't want to forget the absolute value, right? I don't think it's going to matter here because we're going from 1 to infinity, so there are no negatives, but just in case. AP test coming up, right? Okay, good job. We're going to be plugging in 1 and b. Now you can see why I didn't want you having infinity here. You've got to plug these guys in. Okay, so the antiderivative is ln b minus ln 1. Absolute value 1, technically. What is ln 1? 0, correct. Good. Okay, so this problem came out to this. Limit as b goes to infinity, ln b. Notice that we now are doing a limit problem. So the nature of an improper integral problem is you convert it to limit of a difference in antiderivative. So you end up doing an antiderivative, and in the end you have to answer a limit question. So this is like integrals and limits together, you could say. So hopefully you can do this one without any rules, like L'Hopital's rule, whatever. It's not really a fraction. But can you tell me what happens to an ln curve as its argument gets bigger? Can you picture ln? You should know that graph really well. What does ln look like? Rising, right? ln looks like this. And it doesn't really approach an asymptotic. If it has an asymptote, it's here. It's not rising towards a y value. It's actually going to rise to infinity and beyond. Okay? So this actually is infinite. So what does this question mean? Now you may have already guessed this answer, okay guys? Here's what we just did. We took an old familiar curve and we just integrated from 1 all the way to infinity. Did we really expect to get a finite area here? Did you expect to get 4?
Yes.
You probably expected to get infinity. Look how big the area is, right? But be careful. As we're going to see, sometimes, even though this region is infinitely wide, it has a finite area. Here's what I did first period. I took an object like this, and I erased the middle 1/3. So I did it this way. This is called actually a Koch snowflake. Okay? It's called the Koch snowflake. Maybe you saw it in a geometry book once upon a time. And then I'm going to add segments here, 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 and here. Now I'm going to go in and erase, again, the middle 1/3 of every side. Like this. So I've got a lot more erasing to do, and a lot more drawing to fill it in. But it's going to look like this. Has anyone seen this drawing before? This is actually called a Koch snowflake, or Cook snowflake, I think is how it's pronounced. Not too great looking, but you know, what you could do is you could go through and take each straight segment and erase the middle 1/3 and repeat this pattern. So what would happen is your perimeter, if you kept doing this forever, it would be a fractal. The perimeter would be approaching infinity. It's so jagged, it's completely non-differentiable everywhere. If you zoomed in on one point, you would literally find that there's no slope anywhere. Because every time you zoom in to look at a segment, you find it's broken. You see? But would you say that this has an infinite area? No. If it had an infinite area, wouldn't it fill the entire universe? But all I'm adding on to this is smaller pieces than I had before. See? Every time I add these little nodes onto here, I'm contributing so little area that this will always stay bound within a certain size circle. This will never grow that big. So even though it has an infinite property, perimeter, it does not have an infinite area. The same is true for problems like these. You could actually get a finite area. It's possible. This one we proved is infinite. All right, let's try another one real quick. We might have a different result on this one, right? Okay, so let's say you want to integrate from 1 to infinity 1 over x to the 1.1. 1.1. So let's make it proper. Okay, so we're going to replace that infinity with a b, right? I have no idea how some of you are going to pass the AP test. If you don't pay attention, you're not going to pass it. Or if you pass it, you get a 3. I don't think that's what you're here for. apologize if I'm going too fast, but you can at least work on your homework from the other two lessons. If you don't like lectures. Okay, so we made it proper. Okay, now let's talk antiderivative. So if you want to do the antiderivative, you might want to write this, as, I think I would probably want to write it as x to the negative 1.1, because I'm supposed to be adding a power, right? So I like to always write it like that. So I'm going to be adding a power. What am I going to add? Add 1, right? Add 1 to the power. What's it going to be? X to the what? Negative 0.1. And then what am I going to put in front? Let's put the reciprocal of that in front. Negative 10. Let's double check our work. Is the derivative really x to the minus 1.1? Multiply this down, you get 1. X to the minus 1.1. Yes. Good. Okay, we've got the right antiderivative. Let's pull that 10 out. Let's pull that negative 10 out.
Wait, you can do that?
Yes. You can pull it out of both integrals and limits and parentheses, so we're good. This is b to the minus 0.1 minus 1 to the minus 0.1. I've already plugged in the b and the 1. Okay, so this is my answer. Awkward. I have 1 over the 10th root of b minus 1. That's an infinity. That says 1 over the 10th root of b, take away 1. What happens to 1 over the 10th root of b when b gets huge? This is going to go away. The answer to this problem is 10. Interesting. Let's look at this scenario. A minute ago we did this problem. Y equals 1 over x. And we were trying to find the area from 1, literally all the way out to infinity. And we said that this red area does not exist. It does not work. We get infinity. But then, lo and behold, we just add a tiny bit of power to the bottom. And instead of 1 over x, we make it x to the 1.1. And all of a sudden, this area is 10. Interesting. A minute ago, when it was just 1 over x to the first, it was infinite. And now we've got just a hair of power at the bottom. And what's going on is this. You just made this slightly more bottom heavy, which made the curve attack the x-axis just a little faster and pinched off a finite area. You take away that 0.1, and that area is infinite. Put it back in, area is 10. What do you suppose would happen if I made this 1.01? 100. That's right. This would have been 100. This area. Okay? Which is quite large. It's quite a bit of area. So what's going on here is this. The antiderivative here is bottom heavy. Bless you. See, the antiderivative here is bottom heavy. See, it has a minus power. You added 1, but the original power was negative 1.1, right? So when you added a power, the antiderivative came off bottom heavy. And the limits, even though these are big, these vanish, giving us finite area. A minute ago, before there was 1.1, what was the antiderivative? Let's look back at the previous slide. What was my antiderivative? ln, right? This was ln, which actually grows. So the antiderivative was growing, see? But when we do this problem, the antiderivative, not just the function, but the antiderivative is actually bottom heavy. It too is a decreasing function. so it pinches off a finite area. This is why we believe ln is the slowest growing function. Okay? It's a top-heavy function, but barely. Okay? Its derivative is 1 over x. If its derivative is 1 over x plus, like, x to the 1.1, then it wouldn't be the slowest growing function. Okay? So this is kind of a sophisticated argument. It's going to show up in chapter 9. But what we did was, we proved that that area, even though it's infinitely long, the area is 10. Interesting. Yes?
What would be the slowest growing function if that changed? Like it's not going
I don't know. It technically would be log base. I don't know. I'd have to think about it. But we believe ln is the slowest growing function because you know how everything has an antiderivative. X to the first has an antiderivative. X to the 0.1 has an antiderivative. X to the 0 has an antiderivative. X to the minus 1, that's ln. That's the odd man out, isn't it? You ever notice that? Like when you do antiderivatives, you can add a power, but not when you have x to the minus 1. If you have x to the minus 1, you cannot solve it by adding a power. Can you? This is x to the minus 1. Did we solve this by adding a power? No. So this function is the cutoff function, and it forms the slowest growing one. Slowest growing antiderivative. So let's go to just this last example, and we'll just get it set up. This is the one I chose for example 2. You can see it's definitely not proper. It's improper. What makes it improper?
negative 50.
Yeah, that limit of integration. So let's put a limit in front instead, and we'll replace that with an a0. And we'll make a go to negative infinity. It's kind of a formality. Write it in proper form. Alrighty. Okay, why don't we write this as x minus 2 to the negative third. I think we can solve this by adding a power. Okay, so if I add 1 power to my existing exponent, it goes from negative 3 to negative 2, right? And then you'll need the reciprocal out front. So negative 1/2 x to the minus 2 to the minus 2 is really the antiderivative of x minus 2 to the negative 3. You can check it. If you take the derivative of what I wrote on this last line, it really is x minus 2 to the negative 3. The derivative of the inside is 1, so we're good. Let's plug in a and 0. The limit, by the way, is the last thing you do. Oh, I accidentally switched those guys around. Thank you. Thank you, Lauren. I got the a down here, the 0 up here. Yeah, that would have caused a negative error. Thank you. So we're going to end up with, if you plug in 0, you're going to get negative 1 over 2x squared minus, and if you plug in the a, you're going to get negative 1 over 2a squared. You can check my work later, because I'm running a little low on time. There's a double negative there, but you know what? It doesn't really matter, because if a is going to grow big, negative infinity, if a is going to go to negative infinity, this is just going to go to 0 anyway, so I don't really care about this whole second term. How did I get an x here? Oh, I think I did something wrong. Let's go back a step. Sorry, guys. I was going to plug in the 0 for x, right? So it's negative 1/4 minus negative 1 over 4a squared. A minus 2 squared. There we go. I think I got it right.
So it'll just be negative.
Hold on. This is a 2. This is an 8. Is that right? Okay, sorry about that. I think my work is wrong in my notes. The answer to this problem is negative 1/8. All of this just goes to 0. So if you drew a picture of this, you'd see this is really an infinitely large area, but it's finite area. It's got a finite value because it's pinched so tight. So it's infinitely long, but it's got a finite area. Interesting concept. Okay, you guys have a good day. Study hard.